Hello, everyone, and welcome to the first technique of integration by substitution. Remember, the goal is to find that family of antiderivative for a specific function. The first thing you should always try is to use basic formulas and basic properties. But as soon as your formula is more complex than basic stuff, you have to use a technique. And here, this is very different from differentiation, where when it's not a basic formula, you just look at the algebraic structure. If you have a product, you do a product rule. If you have a quotient, you do a quotient rule. If you have the composition of two functions, you use a chain rule. Sadly, the algebraic structure of your formula is not going to dictate which techniques of integration you have to employ. So normally the first strategy is to use the following idea. You want to make a change of variable that will simplify your integral. So you start with a formula typically that depends on x, which is quite complex, but maybe there's a way to do a change of variable that will turn this complex integral into one that is way simpler, and hopefully, like in most of my examples in this section, to the point where it's going to transform into something that is basic. So here are the steps to follow. So the first step, the most important step, is to create that new formula. To make that change of variable, you need to choose a little chunk somewhere in your formula, and you're going to call that little chunk that I call g of x in general, you're going to call it u. And this will be your new variable. Your goal will be to transform this new integral as a function that will depend on you. So the first step is very straightforward, because you're going to say, okay, a u little chunk, you're going to be called u now. But of course, the rest of the formula will still have some x's around, and the goal is to get rid of all the x's. This is almost like a life advice, but anyways, so your goal is to turn this integral into a new integral where the only variable is going to be u. And of course, what is the little chunk that you're going to choose? That's a trickier part. If you choose the wrong part, you're not going to be able to simplify it if the question is a u substitution question. I will make some comments on which part you should try first at the end of these little steps. So once you've made your call, once you know, okay, I think this is the right part of the formula and this is u, the second step is purely computational. You don't look at your integral anymore. You just look at your g that you freshly chosen, not computed. You chose that g of x to be u, and then you just compute the derivative of that formula. So you have your little chunk, it's called g, then du dx, u prime, the derivative of u with respect to x, is going to be g prime. So you compute that g prime. And now what you do in every single question, you look at your du over dx, and you look at it as a little fraction, and you isolate dx simply by doing this cross multiplication. So you just swap the dx and the g prime, so they just change places. And this is going to give you a formula for dx, which will always be du divided by g prime. So now what you do in your formula is that you have a big integral. Remember, in any integrals that you have to compute, the last part is always that little dx. And now what we have is a nice formula. So we're going to get rid of dx, and that dx will always blossom into du over g prime. So far, one chunk of the formula just gets replaced by u, and then the dx gets replaced by the computation of du over g prime. And then if you've done the right work, so if in your integral you replace g of x by u, so your little chunk that you chose by u, you replace gx by u, you replace dx by du over g prime, what will happen is that things will simplify to the point where you're going to have a brand new integral that will only depend on you. So if your substitution is done correctly, if your du over g prime is computed correctly, after you simplify everything, you will have a brand new formula, and that brand new formula will be an easier integral to compute. Typically, it will be easier to the point where it's going to be basic. And I have a little cloud down here that I want you to read. For this class, every substitution, every question that can be done by substitution will either end up as the integral of u to the power n, which will turn into u to the power n plus 1 over n plus 1 plus c, assuming, of course, that the power of u, which is n, is not minus 1. In the case where you have minus 1, your formula will look like the integral of 1 over u du, which is ln of u plus c. And then if you have an exponential function in there, the integral of e to the power u du will be eu plus c. So every question will look like one of those three integrals up to a multiple maybe, but this is the goal, is to get one of those three basic integral now with respect to u in order to get your integral going. So once you know which one you have, you just integrate. Of course, your formula is now a formula that depends on you. So the last step is just to get rid of all the u's and replacing them by g of x, so that your final answer, your family of antiderivative, is an equation with a bunch of x's in it. Okay, so the x's, they come back. Okay, even if you try to get rid of them, they do come back. All right, so now here's a list of common substitution that will be very efficient for you, that you should think about. The big general, if you were like really into integration and trying to use this technique for like a larger class of function, normally the intuition should be that whatever you choose for u, it should be a formula such that if you compute g prime, you see the derivative of g prime somewhere in your integrand that is hanging out near the dx. And I will always make that remark. If you don't like that remark, it's fine. If you use what I have here for the common list, so if you see some big formula to some power, maybe using that formula inside that big powering is the right substitution. If you see a fraction, choosing the denominator, or choosing that denominator that is raised to some power, or if you are a purist, so if you have n that is negative, so if you have a power of a formula, maybe use that formula for g. If you see e to the power of some shit, okay, probably trying the exponent of that exponential function is the right move to do. In general, the idea is you try to find an inside function. Typically, this is not always true, but typically substitution is kind of the reverse of a chain rule. And when you do verification for your computation, most of the time, you're going to be doing a chain rule to verify if your answers are correct when you're doing a u substitution. Anyways, a lot of information. I'm fully aware of that. The best way to digest this information is by jumping into examples. All right, first example. Let's compute the integral of 2x times e to the power of x squared dx. Big complicated formula. This is not basic. We have to use a technique. Let's try u substitution. I think here, if you're comfortable with that list of tricks, you see an exponential function, you see that the exponent is a formula. In this case, it's x squared. Maybe this is the best candidate for my u substitution. So let's try it. Let's say that my u is going to be equal to x squared. And to some extent, and this is fine for notation, I think this is one extra step, but sometimes it helps understanding what's going on here. So you could simply say, hey, I'm choosing x squared to be u. So my integral now at this point is simply 2x e to the power u dx. So there's still a bunch of x's around that you want to get rid of, but right now the exponent simplifies to u. Now let's try to simplify this by following the steps. So now that we've chosen my exponent to be x squared, I'm going to compute the derivative of x squared. So I'm not looking at my integral, I'm just looking at my u formula, so u equal to x squared, and I'm computing its derivative, and derivative of x squared is, of course, 2x. And now the idea, and this is the goal, the next goal is to always get rid of dx. We need a formula for dx. So just by swapping the 2x and the dx, you get a nice, clean formula for dx. So the dx is going to be replaced by du over 2x. So my next step here, So I have 2x, it's still 2x, EU is EU, but now dx, boom, it blows up into du over 2x. But see what's happening now? Nice. So here what happens is that those two x's will cancel each other, and you're going to be left with what? This brand new, super clean, super simplified, basic integral, the integral of EU du. And now we can use that basic formula, and we're going to get EU plus C. And the last step is to simply replace the u by the original substitution formula, which is x squared in this case. So EU will turn into e to the power of x squared plus c, and that's your final answer. And what's kind of neat, you can do this for verification. If you compute the derivative of your answer, what will happen? Oh, that's a nice little chain rule. We have e to the power of some shit. So you're going to get e to the power of that shit times shit prime, which is 2x. Meanwhile, the derivative of c is 0. What a coincidence. This cleans nicely, perfectly back to 2x. If you put the 2x first, e to the power of x squared, which is exactly your integrand, your formula in your question. So this is something, if you have time, take your final answer, compute its derivative. If things are done correctly, you're going to get back the formula in your question. This is amazing. More. Okay. All right, the next example, let's compute the integral of x cubed over 1 plus x4 dx. So here we have a quotient of two things. There's no quotient rule. I want to do a substitution. So I have to pick a chunk of the formula in order to call it u. Here I can see that my denominator is probably a good choice. So what about choosing 1 plus x4? And the reason why I would want to choose 1 plus x4, if I rearrange this equation, I can write x cubed over 1 plus x4 as 1 over 1 plus x4 times x cubed. So if I call 1 plus x4 my u, I'm going to get 1 over u, and I know 1 over u, which is ln of u in absolute value plus c, is a basic formula. So let's try to use the denominator. So just to be clear, if you like to do this in 2 steps, you get, at this point, you're just choosing the denominator to be u. You're still stuck with x cubed, but the strategy is to get rid of the x first. So you go back into your little box there. What is the derivative of 1 plus x4? It's simply 4x cubed. Then you do your swap. It's always the same move algebraically. You bring that 4x cubed under the du, and this is going to be the formula for dx. So you replace dx by the freshly computed formula. So x cubed for now lives. And then what is dx here? Now it's du over 4x cubed. And this is when you have this good sensation inside. Yes, those two x cubed will cancel perfectly. And then you're going to be left with the integral of 1 over u times du over 4. And if you really want to see your basic integral, that over 4 is just a coefficient. So you can kick that coefficient outside so that you can really enjoy that pure basic formula. Now the variable is u, but that's just a symbol. So 1 over u du, the integral of 1 over u du, that's your basic integral. And you know it's going to turn into ln of absolute value of u plus c. And as usual, the last move is to replace u by its original formula, ln of absolute value of 1 plus x4 plus c. And that's your final answer. And again here, you can do your little verification. If you compute the derivative of 1 over 4 ln of absolute value of 1 plus x4, the absolute value plus c does not change anything. So if you have ln of some shit, okay, you're going to get 1 over that shit. So here 1 over 1 plus x4 times should prime, so 0 plus 4x cubed plus 0. And here again, by the power of simplification, you can see that the 4 cancel each other. You're left with 1 times x cubed. So this will clean itself very nicely, very nicely to x cubed over 1 plus x4. What a coincidence. This is exactly the same formula as the formula in your original question. And again here, you should notice that in that verification, we had to use a chain rule. And this is very typical when you're doing use substitution, that if you are taking the time to compute the derivative of your answer, that you're going to have a chain rule in order to get back your original formula. And again here, we do that substitution to get back one of those basic integral. In our first example, we had EU that went to EU plus C. Now we have 1 over U that went to ln of U in absolute value plus C. So we just need one more example to cover all 3 basic formula. So that will be my next example. Next example, just to have that sense of completion, we have to integrate 2 over x square root of 1 plus ln of x dx. So again, here we have a quotient of 2 things. Trying the whole denominator for the u, if you think about what you're choosing, you have to remember that you also have to compute its derivative. And if you choose x square root of 1 plus ln of x as u, this means that the u prime is a product rule. This is typically a sign that this might be too complicated. So what should we choose? Well, we have the square root of something. Remember, square rooting is a power where the power is minus 1/2. So just to illustrate this clearly, that square root of 1 plus ln of x, I'm going to just rewrite it as 1 plus ln of x, all that to the power 1/2 at the denominator, and bring it up as a power minus 1/2. And also this will build the intuition that if you are taking this term up, you are leaving behind that x at the denominator that you can write as 1 over x dx. So if you choose 1 plus ln of x as u, what is the derivative of 1 plus ln of x? Well, it's 1 over x, and it's right there, 1 over x, waiting next to dx. This is a strong indication that this is the correct substitution. So let's go, let's try this. So let's go with u equal to 1 plus ln of x. So in my integral at this point, I have the integral of 2 u to the power minus 1/2, and then 1 over x dx is waiting. The next step is to get rid of dx. So this is very algorithmic. So to get dx, I go back to my u formula. I compute the derivative of 1, which is 0, plus the derivative of ln of x, which is 1 over x. Now, if you cross multiply these things to get a formula for x, instead of bringing the 1 over x down directly, I will cross multiply, bring the x up next to the du. So I have x du is equal to 1 times dx. So that's going to be my formula for dx. So the dx will simplify very nicely to, so we have u to the power minus 1/2. So 1 over x is 1 over x, and the dx blossoms into x times du. And again here, nice, the x's, they cancel each other. I will even bring the coefficient outside, just to focus on my basic integral. It's a simple power rule now. I have to integrate u to the power of minus 1/2. So apply my power rule formula for integration. So I get 2 minus 1/2 plus 1 will be 1/2 divided by the same power, 1/2 plus c. And now if you divide by 1/2, that's the same thing as multiplying by 2. So you get 4 times u to the power 1/2, but where u is replaced by its original formula, ln of x, 1 plus ln of x to the power 1/2, or the square root of, plus c. And as an exercise, I strongly suggest that you verify that this derivative of this answer will give you back the formula inside your integral. So we did 3 examples, a EU, a 1 over u, and u to the power n. So making a u substitution. In every single example, you should see that there's a tight relationship between the formula that I've chose. Like in my first example, I chose x squared degree 2, and the derivative was 2x, which I had perfectly in my first example. In my second example, I chose the denominator, which was a degree 4, and I had the degree 3 waiting up there at the numerator. And now for that example, I had 1 plus ln of x. The derivative of 1 plus ln of x is 1 over x, which I also add nearby. So the meta idea in this u substitution is you're choosing a chunk such that its derivative is out there up to a multiple. But if you want to put it simply, trying the exponent of the exponential function, trying the denominator, or trying something inside a power will work at some point. So if this is a u substitution question, this is the way to get there. But anyways, for this first video, we'll do more examples in the next one. But for this video, that's it. That's all. Bye-bye.